Okay, so should I start, Jackie?
Yeah, please.
What's the tradition, or do we wait another minute or two? Or?
I think we're okay to start if you'd like.
Okay, so let's get started then. It's a great pleasure to introduce today's speaker in the distinguished lecturer series of IACS. Today's speaker is Professor David Keyes, a professor of applied mathematics and computational science and the director of the Extreme Computing Research Center. He has served as the dean of the Division of Mathematical and Computer Sciences and Engineering, excuse me, at KAUST for the first few years, the inaugural years of that division. And he's also adjunct professor and former Fu Foundation Chair Professor in Applied Physics and Applied Mathematics at Columbia University, and an affiliate of several laboratories in the US Department of Energy. David graduated in aerospace and mechanical sciences from Princeton University, and then earned his PhD in applied mathematics from Harvard. And I've had the opportunity to meet David in several conferences, and also several times in the corridors of Pierce, which he visits often, or at least visited often before the COVID lockdowns. And it's great to see him again today, that he joins us for this lecture. It's too bad we couldn't meet in person. David has made seminal contributions at the algorithmic interface between parallel computing and the numerical analysis of partial differential equations, with many key papers in the field, and he's very well known. Actually, he put together a wonderful team that wrote a very nice review paper, Multi-Physics Simulations, Challenges and Opportunities, a few years ago, and I was part of that effort. So it was really wonderful to see his leadership in the field and his key contributions overall. So I'll stop here and I'll yield the floor, or rather the screen, to David.
Thank you so much, Tim. That was very kind, and I do wish I could be in the new Alston campus to see you all, but we all are used to this technology, and the snowstorm has done what COVID could not to keep us apart today. It's my pleasure to speak about data-sparse linear algebra for large-scale applications on emerging architectures on behalf of a rather large team at KAUST. We call ourselves HICMA, for hierarchical computations on many-core architectures, but it's also the Arabic word for wisdom. And I think many of you will agree that hierarchical algorithms like the FFT, the fast multipole method, multi-grid, sparse grids, and so forth, do embody collected wisdom. And my job in the next hour is to similarly elevate hierarchically low-rank methods of linear algebra. These methods do not need any push from our team. They are highly compelling and very much visited in SIAM and ACM and other meetings these days. And they are bringing a renaissance of numerical linear algebra to high-performance computing. Before I turn to the topic, I just want to note that the connections between Harvard, the oldest university in the Americas and one of the newest in the world, go deep and back to the beginning of KAUST. The founding president was Chun-Fong Shi, a student of John Hutchinson in the predecessor of Harvard SEAS. And as Tim mentioned, he recruited me as one of his founding deans. We have many collaborations, in fact, between the two institutions today in materials science, in scientific visualization, and many cross-appointed alumni. My conclusions up front, so that you can decide whether you want to stay, is that with controllable trade-offs, many linear algebra operations adapt well to high performance on emerging architectures such as GPUs and other accelerated heterogeneous nodes, through higher residency on the memory hierarchy, greater single instruction multiple threaded concurrency, and reduced synchronization and communication. And in this effort, rank structured matrices based on either uniform tiles or hierarchical subdivision play a major role. And the software is here. A lot of open source software for shared memory, for distributed memory, and for GPU environments exists. And many applications are benefiting, not just by the 10 or 20%, which is often enough in a week-long running thing that hogs the supercomputing, but literally by orders of magnitude in footprint and runtime for many classes of problems. Rank structured operators are able to tune the amount of linear algebra work you do and the amount you store to the overall accuracy requirements, which may, of course, come from truncation error, or they may be, the linear algebra may be in the inner loop of an outer nonlinear loop with progressive tolerances as one gets closer to the solution, and it would be wasteful to solve the linear problem to high accuracy. And they do this by shrinking the memory footprints to live higher in the memory hierarchy, in cache, in registers. And this means, of course, better arithmetic intensity, more flops executed for the precious resource of bandwidth. The disadvantages are that one has to pay the cost of that compression. There are many different ways to do it, but not all operators compress well. For instance, random matrices hardly compress at all, but many matrices coming from physics and other applications compress extremely well. The idea is to replace dense blocks, all-to-all coupling, with reduced rank representations like multipoles, whether these are born dense or whether they arise during matrix operations, such as partial elimination during a sparse matrix factorization. One can use high accuracy to build exact solvers, low accuracy to build preconditioners. One can consider hardware parameters in tuning the block sizes and the maximum rank parameters, such as cache sizes and warp sizes. One can use approximate SVD methods, such as the randomized SVD, very popular from 2009, rather than the full n-cubed SVD. Even on the small blocks, the n-cubed will hurt you. And of course, the randomized SVD is a flop-intensive and flat gem-based algorithm, so it runs very close to peak. We can implement these on batches of leaf blocks for uniformity in SymT, and in the case of trees, in the recursively subdivided hierarchically low rank, we can flatten the trees. Now, there are two types of rank structured matrices. And by the way, I use that in the same way that we use sparse matrices going back to Wilkinson. A matrix is sparse if there's enough non-zeros to pay attention to them. And it's rank structured if the blocks have low enough rank to take advantage of them. Tile low rank considers all the blocks at a single level of subdivision, which could in principle vary in size, square down the diagonal, but different sized. Hierarchically low rank blocks are left at various size levels upon recursive subdivision, and they come in weak and strong admissibility variants. These are the same concepts used in the fast multipole method. For some degrees of freedom to be well separated, their diameter should be small compared to the distance apart they are. So these are two one-dimensional examples of a weakly admissible thing where the blocks go all the way to the diagonal. So this block might have a high rank, whereas these blocks would have more or less uniform ranks as they grade away from the tight coupling on the diagonal. Hierarchically low rank is actually more than 2 decades old. It was introduced by Huckbush, the same Huckbush who gave us multigrid in the 70s, and Tertishnikov simultaneously. The concept goes back to Miroslav Fiedler with his structured ranks in 1993. To conceptualize how these are generated, this is not the right algorithm, but this is a way to think about what you get in the end. You start with a full matrix and you ask, is this globally low rank? And if not, you can subdivide. And eventually you set a block size B, which is acceptably small to handle in a dense way, and a rank threshold K that is acceptably small to justify the compression cost. And eventually the outer diagonal blocks shown in step 2 have a small enough rank to leave them as they are, whereas the next level to the diagonal needs to be further subdivided. And so this recursion basically says, compress to required accuracy. Is the rank acceptably small? If not, subdivide and recur, and ultimately take the union of the leaf blocks, some of which are left dense here in red, and then we have low rank blocks of different sizes. And therefore, the union of all those leaves gives us a representation of the full operator. So the way I've described it is not efficient. It's better in practice to compute the tree structure in advance, which we can often do from physical principles. Now, data sparsity can be illustrated very simply from the 1D Laplacian, which in its forward representation is obviously both sparse and hierarchically low rank in the sense that off-diagonal blocks have low rank. But the fully dense inverse is also data sparse. You recognize that the columns of this inverse are just the Green's functions at different locations of the original Laplacian. And just as this off-diagonal block has rank 1, so does the off-diagonal block of the dense inverse. And in fact, Fiedler showed back in 1986 that conformal off-diagonal blocks of these matrices, of any matrix that has invertible off-diagonal blocks, admit the same low-rank representation. The complexities of rank-structured factorization are very attractive compared to the order n cubed operations of an order n by n dense matrix or its n squared storage. By tile low rank, we can replace a power of n with a half power of the typical maximum block rank k. And with the full hierarchically low rank, we can be left with just order n log squared n operations times a k squared. And in storage, you can get down to linear in n storage with hierarchically low rank. This is also relevant to sparse problems because when you factor them, they fill in. For example, a 3D Poisson solver on a cube with a classical nested dissection ends up with a separator, which is of size, if this O of n is little n cubed, then the size of that separator is little n squared, or n to the 2/3. And therefore, if we put that into a dense elimination just on that 2D separator, we have an order n squared complexity. And with the tile low rank, replacing that cube of the dense elimination on the separator with just the square, that can be reduced to the original degrees of freedom down to the 4/3. And indeed, with hierarchically low rank, it goes all the way down to linear in n. And the gains come from recognizing that the recursively constructed Schur complements from this potential problem have low rank. So the key question is, what is k? If we're replacing n's by k's, what is k and how is it affected by the accuracy we require in the blocks that are so approximated? And it turns out that for a given k level approximation in the 2 norm, the rank scales like log of 1 over epsilon to some near unity power. So if we square the tolerance from, let's say, 10 to the minus 3 to 10 to the minus 6, we only double the rank. Now, for purpose of batching many identical subproblems on GPUs, we will eventually choose a maximum k for this complexity. And the k that you need to bound the accuracy of a given block is given by the largest neglected singular value in your SVD. Now, it's not straightforward to go from the blockwise accuracy to the overall accuracy from a given downstream operation, such as a matrix solve. And this is actually an area where some theory is needed, but there's a lot of operational facility with choosing good ranks. So what types of matrices are candidates? Matrices arising from covariances in statistics, with decay with distance, integral equations with displacement kernels, Schur complements from elliptic or parabolic PDEs, Hessians, from PDE constrained optimization, non-local operators from fractional diffusion, radial basis functions from unstructured meshing, and very opportunistically kernel matrices from machine learning applications. So applications that may possess memory capacity constraints like geospatial statistics or PDE constrained optimization, energy constraints like adaptive optics for remote telescopes where you don't have a lot of power for a supercomputer to adjust the tens of thousands of little actuators that correct for the image, real-time constraints like in wireless decoding, massive input, massive output antennas, running time constraints like chemistry or materials or genome-wide association studies. And we've been applying it to almost all of these areas, and I'll give some examples from the first three during the talk. So let's take geospatial statistics as a rather timely example because we have so many observations now stretching literally into the millions in many cases, whether it's wind speed or soil moisture or solar insolation, things that we need to improve our handling of global climate, where we have some measurements and need to predict elsewhere in space or in space-time. We may have a million by million dense covariance matrix, which would require 4 terabytes if it is symmetric, 8 terabytes in double if it's if it weren't, and that's how much that is and how long it takes to write that amount, and that would be an exaflop of computing to factor that matrix. Statisticians facing such large covariances typically adopt very drastic approaches, such as trying to find a global low rank or to zero away outer diagonals or remote correlations. Better approaches are to hierarchicalize them and even to reduce the precision of outer diagonals. But we won't talk about the latter today. We're very interested in that in HICMA, but today we'll concentrate on the low rank features. So the overall motivations include the many application opportunities just cited to basically treat larger problems in cache or in GPU. There's a mathematical aesthetic. These rank structured methods are beautiful in the sense that they are variable coefficient generalizations of fast multipole, which is by itself very beautiful if you have the Green's function. There's an engineering aesthetic. You can tune your work and storage to your accuracy requirements and not oversolve. There's a software engineering aesthetic. We're modularizing together a lot of nifty recent ideas, direct and randomized floating point kernels like SVD, tree traversal from FMM, task-based programming models like Quark, StarPU, Parsec, and the like. And of course, there's a computer architecture constraint to meet: limited bandwidth per core and limited fast memory per core in the highest performing systems, just because it's so easy to proliferate cores, but moving data costs energy. To illustrate that constraint, I like to quote Karen Bergman, the optical computing expert from Columbia, who has for a decade been tracking the increasing gap between node compute power and node bandwidth to local memory. This was a study normalized to 1 back in 2010 based on the average of the top 10 systems in the top 500 for HPL. And as you can see, the node power of 31 gigaflops then has gone to more than 4 teraflops, 137 times improvement. Meanwhile, the node bandwidth went up only by a factor of 6, resulting in a large deficit in the balance of getting data to the processors. And the last 3 number 1 systems in particular, Taihu Lite had a very bad imbalance, which Summit made far worse. Fugaku actually made a drastic improvement and raised this monotonic deterioration of balance all by itself when it came online in 2020. But remember that Fugaku costs $1 billion, and not every scientific computing lab can afford to create that balance of bandwidth and flops. So now we have two universes of numerical linear algebra really existing side by side. There's the textbook universe of flat memory, where accessing any piece of data in a large matrix costs the same, and where we can use global indices to express our algorithms. And then there's the reality of the way they have to be encoded to respect memory hierarchies, where we have that, that IJ within a block, but we have some organization of those blocks that is more memory friendly and outer traversals of them. So from a brown field to a green field, algorithms were once flat, a la, for example, the Cholesky decomposition. Cholesky was a surveyor. He had all these positive definite least squares systems. And in 1910, he invented the famous triple loop triangular factorization with order, n cubed over 3 flops. And, in those days, we didn't even have digital computers, and all memory elements were equidistant. Architectures were once flat. Von Neumann, designed his architecture in such a way that, under the assumption basically that computation was more expensive than going to memory. And one hierarchy is not so bad. As humans, we might say, okay, hierarchical algorithms on flat architectures, I can code that. Or we might say, okay, flat algorithms, if you insist on handing me messy, heterogeneous devices. But two independent hierarchies of optimal algorithmics and realistic architectures may not automatically match. We may need to marshal irregular structures into uniform batches, feed dynamic runtime queues to overcome dynamic load imbalances. And this is really a path forward for heterogeneous architectures. So our philosophy in the HICMA group is that we have to span a widening gulf between ambitious applications and austere architectures. Energy austere is primarily the driver through adaptive algorithms. And we see this as a full employment program. And any young scientists watching this, I hope you will certainly agree that the stretch between larger and larger, less regular problems and more heterogeneous, but highly structured instructions in computing give you a lot of creative room. So we must address this tension between hierarchical algorithms with their irregularity and adaptability and the highly uniform vector matrix tensor and general SIMT operations. For example, in tensor cores doing 64 operations in one instruction to convolve together two 4x4 matrices, a kernel of convolutional neural networks. So we have hierarchical algorithms, a lot of mathematical richness, GPU and many core, a lot of architectural development, and to make one fit on the other is a very interesting target. And literally, we might as well not go to exascale unless we can crack this one. We might as well stay at petascale. Otherwise, we have to move billions of dollars worth of open source scientific software, where linear algebra is often the dominant inner loop cost. So we have to meet hierarchy with hierarchy. Now, many people have been addressing this. This is a list of some software that I'm aware of that leverages data sparsity. The very first example actually is Bebendorf's in 2005. And then there's a multi-year gap. And then the sort of the floodgates open around 2013. But I have to tell you that a lot of this is just scalar code. Some of it is even MATLAB code. Not a lot of it is distributed memory, and not even a lot of it is optimal on a many core shared memory. So that we took as a challenge for HICMA, where we basically replace a lot of the n-cubed BLAs with our own BLAs and a hierarchically low rank or tile core. Still building, of course, on the vendor provision of highly optimized dense BLAs for the innermost blocks. And of course, still using vendor optimized message passing and multi-threading. We have a lot of code at GitHub in the Extreme Computing Research Center. ExaGeoStat, which actually has an R interface to a supercomputer for geospatial computations. The multi-objective adaptive optics software, which is in the Japanese Subaru telescope in Hawaii and being planned for the European Extremely Large Telescope. Our KAUST BLAs, which have been part of the NVIDIA cuBLAs for about 7 years. The KAUST SVD, which is part of Cray's LibSci for the past couple of generations of that library, and some Cartesian mesh traversal software for explicit updates, which is part of Aramco's ExaWave for seismic inversion, along with a multi-level buffer system that generalizes two-level cache protocols to a deep memory hierarchy, and some of these other things that they're still in the process of promoting. The design strategies of HICMA include embracing dynamic runtime systems based on task graphs, many examples out there. It's like message passing before MPI. There's not a standard yet that works across CPUs, GPUs, shared, distributed, different precisions, and so forth. But these kind of there's sort of a falling out, an evolution that's occurring that's very productive. We want to co-design libraries to diverse architectures so that users can deal with a high-level API and connect to many different devices. And of course, exploit the data sparsity that lets us live high on the memory hierarchy, if you will, to meet the curse of dimensionality with the physically endowed blessing of low rank. So I'll just briefly mention the first two because I need to refer to them. Taskification based on DAGs removes many artifactual synchronizations in the form of subroutine boundaries or enumerated nested loops, which, if you interpret them literally, impose unnecessary ordering on a lot of potentially concurrent operations that are exposed by the DAG. One must pay the overhead of managing the task graph, building it on the fly and consuming it on the fly. And if one wants to exploit the extra concurrency and address the load balance, one might lose some memory locality. So it's a trade-off. But how it works is the following. If you look at, for example, this 4-stage algorithm for a generalized eigensolver, where we first Cholesky factorize the B matrix, apply its inverses to get a standard eigenvalue problem, then try to diagonalize the resulting left-hand matrix, and then do QR. The first 3 of those are flop intensive, and they have the task graphs shown on the bottom, where the height denotes the time, the different steps, sequential steps, and the width denotes the potential concurrency at different stages, and this is for a 4x4 blocked system. We can eliminate those subroutine boundaries and get a shorter critical path and a wider potential concurrency. And this is, what we aim for in a wide variety of linear algebra operations. This has been around since, I think, around 2006. I think Hatem Altayev is on this call. Tile algorithms in Jack Dongera's group, I think, go back that far, but are now catching on quite universally. We also want to co-design to diverse architectures, creating large numbers of small problems that are uniform, that can be marshaled into GPU warps or many cores. A polyalgorithmic approach based on available block size, and taking advantage of such coding tricks as non-temporal stores, when writing back to cache, coalesced memory accesses when loading, double buffering, all to reduce sensitivity to memory latency. The code is more complex. The code is architecture specific at the bottom, but it gives us the hourglass philosophy of many applications using many different architectures through a common algorithmic infrastructure. And with respect to tile low rank, that begins with ordinary tile algorithms. So tile algorithms were the successor to the Scala-Pack two-cyclic block algorithms of LinPack. They became popular in the middle of the first decade of this century. You divide the matrix into many tiles, and you find those tasks that can be fired once the traditional down the diagonal ordering is followed. And say, for instance, a Cholesky factorization, there are going to be 4 of those green block diagonals factored. After each one is factored, the tridiagonal solves are going to be applied to the blocks underneath the factored diagonal, and then some symmetric rank K updates, and then gems to propagate the elimination across the rows. And so you can see how many of those operations and many different colors can exist at the same time if we unroll this loop appropriately. Well, in tile low rank, all we do is we replace the 2 most intensive of those operations, namely the SYRK and the gems, with their low rank counterparts. We terminate the construction of those dense matrices with an SVD representation. This can be done with fixed bounded rank for preconditioners, where the accuracy is more or less a function of what the data is in that block, or it can be done adaptively to find the appropriate rank for uniform accuracy. The dense tile Cholesky factorization does not save you any flops or any memory. It only improves the scheduling. The tile low rank version, actually, though, if you compare the middle to the last column, it actually replaces some of the block size B's with blocks with ranks within that block, and ends up with an order n squared times rank instead of an order n cubed. And really, this is a matter of addressing the n cubed intensive operations in those inner loops. There are several means of doing the off-diagonal rank compression. The standard SVD is too expensive. It doesn't really save anything. The randomized SVD is very effective. The adaptive cross approximation is even more, it gives you an even better memory complexity, but tends not to be as accurate. If you know a lot about your kernel, it's pretty reliable, but for general matrices, probably go back to randomized SVD. There are skeleton algorithms now that just subsample columns and rows and glue them together with a small block, interpolatory decompositions, as they're called. These are all ways of reducing that B cubed to some lower polynomial. And we offer RSVD and ACA as part of the Kaustblas and our GitHub repo. So let's see the implication for a geospatial statistics application in 2D or 3D, some randomly distributed sample points, observation points, and a subset of them is picked out for prediction from fitting to some Gaussian matern or other kernel. So typically, we do this through a log likelihood estimation. The parameter vector theta represents things like correlation lengths and exponential decay rates in a idealized Gaussian or matern fit. And the sigma matrix there is the covariance matrix of all those correlations between the different observation points. And so this is an optimization problem for the small number of degrees of freedom theta that parameterize your fit, and the large number of observations z. So the sigma matrix can be 1,000,000 by 1,000,000, which, as we noted earlier, is 4 terabytes if stored symmetric in double precision. And so that matrix inverse and that determinant, which can be computed from the diagonal of the Cholesky factors, depend on doing a Cholesky of a large system. So here are some runtime complexities for the conventional algorithm, the classical n-cubed algorithm, and a tile low rank version implemented with star PU on 3 Intel architectures, Sandy Bridge, Haswell, and Skylake. And you can see that the architectural advance alone gives nice improvement. Same algorithm, better hardware, but better algorithm on the same hardware is far better. This is a log scale in the y-axis. And of course, if you are able to run the best algorithm on the most advanced hardware with its higher, flop to bandwidth, constraints and so forth, then you can really win big. The memory footprint compared to that 4 terabytes of the original dense is also a couple of orders of magnitude less. So both in time and accommodation on a small memory system like a single GPU, this is a big way forward. It also applies to distributed memory. This graph shows the Scala-Pack algorithm operating on 16 to 256 nodes, going down here, and then the HICMA tile low rank Cholesky on just the 16 nodes, surpassing the conventional algorithm on a very large system and on the original by a couple of orders of magnitude. Here's a tour de force, just for the sake of argument, with a 42 million degree of freedom covariance matrix that would fill up about 4K nodes of our 6K node XC40 at KAUST. If this were stored in dense double, it would be 14 petabytes, which is actually more disk than we have. And if it was able to be computed at the same rate of the TLR computations, which do in fact terminate here, it would take 77 days to do one Cholesky, and then you have to do multiple of those in the optimization for max likelihood. What does that look like for one of those examples, the dense factorization, 18 seconds, and these are the traces where green is computation and red is idle time during message passing. This is for the dense. This is for the tile low rank. And if you put their scales together, you see two things. Tile low rank is a lot faster, but it is also a lot less parallel efficient. There's a lot more red in the tile low rank because we've eliminated a lot of work, and that non-compressible critical path from upper left to lower right diagonal block is still there. It's overall much less work, much less energy, but it would be you get the wrong idea if you based your evaluation of these two algorithms on parallel scalability alone. This Cholesky for reals, which is enough for statistics, has been generalized to complex LU for scattering, in this case, acoustic scattering of an exterior Helmholtz problem. So the Green's functions are non-monotonic, but there's still a lot of structure to be harvested in them. And you can see here for this particular scattering problem where you see pressure contours on the hull of the idealized submarine, you see different matrix sizes in a boundary integral treatment of this plane wave scattering. And what I would like to point out is the generation of that's common to both methods. If we use a tile low rank method, then in addition to generating, we have to compress. So there is a sort of an extra overhead for compression, but then the cost to solve n cubed versus n squared k is a dramatic savings. And whoops, I don't know what happened there, but if you want to solve a lot of right-hand sides, which you typically do in a scattering problem, different angles of incidence, then the repeat cost in the compressed framework is dramatically less than the repeat cost for a new right-hand side. Of course, we can reuse the factorization, but we still have to do the back solve. And this work was actually a prize-winning paper at ISC 2020, virtual in Frankfurt, where two of my Saudi grad students actually shared this Gauss Award from the German Supercomputer Center. So far, that's all tile low rank, but things get better. Hierarchically low rank can shave away another power or more of those n's in operations and another half power in storage, getting to linear in matrix dimension. Of course, assuming that the k can be tamed, and often it can. So here we are back to these one-dimensional depictions of strong scalability, strong admissibility, and weak admissibility. In higher dimensions, things that are close to each other in space may be far from each other in the Cartesian ordering of that space. So you will find some blocks that have to be left dense that are off the diagonal. It's not quite as simple a structure. There are many flavors that exist. For example, you could hybridize, you could treat one of those green blocks, which is supposed to be low rank in HLR, with a TLR data structure, for example. But ultimately, we need to have a lot of modularity and polyalgorithmicity to balance between optimal memory and compute complexity and the complexity of the implementation. So what sort of SIMT instructions are available and efficient? Here's a typical H2 hierarchical matrix representation. So in H2, we take the bases that would be required for representing each of these blocks, which in the standard hierarchical are computed per block. And we say, let's use a common set of nested bases for everything along a block row. So in order to find the SVD of this block, let's use the U's and V's that come from this collection of finer grained blocks closer to the diagonal. So we're going to have nested bases. We'll build up the bases for the coarser blocks by combining the bases of their children blocks. And this is how you reduce the footprint from order n log n to order n. It's very similar to the same transformation in fast multipole, where you have the reuse of elements at common distances and scales rather than storing each one separately. So we can depict that here, where this is the 0 level, and this is level 4, and the finest leaves are at the coarsest, at the at the 4th level. These little blocks like so, and that's the only place that we store a k-wide basis. So there's kn data here. Everything else in this problem is small, singular value blocks, truncated, small basis exchange blocks, and small dense blocks. Hopefully not more than n over k of them, so that the overall complexity of storage remains nk. There's a large zoology of H matrices. This is not comprehensive, but the main axes are whether you have flat or nested bases and whether you have weak or strong admissibility. So there's the hierarchical off-diagonal low-rank hodler. There's the hierarchical semi-separable. Those were invented at Stanford and Berkeley, respectively. And then there's the strong admissibility H's from the Leipzig school. We'd like to introduce a new piece of software that runs on both shared and distributed, both GPU and CPU, called H2 Opus for the H2 format. The high-level operations are being able to multiply together two hierarchically represented matrices, different ones or powers of the same, and to recompress them. To generate an approximate matrix inverse, for example, via Newton-Schultz iteration, which can use matrix-matrix multiplication, but does not pay for itself if the matrices are dense, or even if they're sparse and the bandwidth swells with multiplication. But now that we have a recompressible low rank, Newton-Schultz actually is a very practical inverter. We can also directly factorize as we with tile low rank, but that is actually being developed at Berkeley now by the Kaus grad student who invented H2 Opus in Sherry Lee's group. And of course, forming sure complements can be done either by directly using the matrix inverse or by randomly sampling that product. The core utilities are matrix vector multiplication, which I'll illustrate, H-matrix construction from MatVex, low rank updates, compression, orthogonalization. All these things are part of the infrastructure of H2 Opus at our GitHub repo. And for GPUs, we batch with Magma, cuBLAS or kBLAS, and with CPUs, OpenMP or Intel's MKL. And this is Waji Bukaram, who created these things as part of his thesis. So it's a performance-oriented library for H2. H2 because we need to fit into the tiny memories of GPUs. So we didn't even want an n log n hanging around. We wanted just straight n. It also runs on CPUs, although here the memory is less at a premium and other methods may do just as well. But for a common coding interface, it's important to have the CPU version. It scales on distributed memory up to thousands of GPUs on the Summit machine at Oak Ridge, for example. It has strong and weak and user controllable structures for the nested decomposition. You can use it to build kernel matrices from specified kernels. It has quite an optimized MatVec, getting up to 80% of the gem performance on GPUs. These are some of the other features. I think I'll just go through these slides quickly and illustrate on some examples. So the hierarchical MatVec is done by tree traversal, similar to the fast multipole tree traversal for n-squared interactions. So informally, you can write this matrix as the red part, which we'll call D, the union of the dense blocks whose locations are known, and then a USV, which is, you can think of as sort of outer products of all those singular value decompositions in the blocks anchored by a blue square of truncated singular values, and on the row and column bases, the UNV in dark for the fine-grained end of the nested bases, and in yellow, the E and F blocks that create coarser bases from the finer ones. So to multiply such a matrix on a vector, you have to first of all use this additive separation. This is a trivial part, and then this part is interesting because of the data structures. So it's sort of a tree-based MatVec. The finest level bases are applied to their corresponding segments of X, and then through the F matrices, those are upchained to the coarser blocks, and then the singular values of the fine and ultimately coarser blocks are applied to these different separated versions of X, and that gives us an intermediate which can be downswept back into U times Y. So this is USV times X, and that's the sparse piece that gets added to the dense piece to give the final product. I should have done this animation rather than moving my mouse around. Now, you've seen this before. This is like the tree-based recursion of fast multipole, and these are figures from Ryo Yokota at Tokyo Tech. The P2P, particle to particle for nearby clusters, is analogous to the dense blocks, and the particle to multipole expansions, the multipole translations, and the multipole to local multiplications. This is like applying the SVDs, the singular values, and then recurring back down to put the things in the right place. How does it compare to FMM? After all, you can create an FMM potential matrix and instantiate it in a hierarchical matrix and do the multiplication either way, based on the physics or based on the linear algebra. Here is the fast multipole, and the memory requirements that it needs are really quite modest, because we're not storing matrix elements, we're just storing, in some sense, the Green's function kernel. If you want to write that out in HLR matrix form with strong admissibility, you get the same order n scaling with problem size as with fast multipole. But of course, you need more memory because you're now actually storing matrix elements or the bases for them. If you go to weak admissibility, you're storing, your ranks are expanding in the larger blocks, which are less well separated, and the memory growth is higher than linear. So it's all sort of as expected. This is an algebraic generalization of FMM. It's easy to distribute it. Different nodes here of the computer have different colors, and a lot of the work takes place in a fully distributed way until you hit sea level in the recursion, just like the coarse grids in multigrid. Eventually, it's not worth distributing the computation, so you go to the root node and then pass on back to distributed at the end of the USVX portion. I like to quote, I like to paraphrase Mark Twain here, where he said, history doesn't repeat, but it rhymes. Hierarchical algorithms do not repeat themselves, but they do rhyme. They have a lot of common infrastructure coming from their common structure. And here is a picture of the distributed upsweep and where it shifts to the scalar, the root node, and comes back. So let's look now at that same geospatial application, but now with H2, HLR, instead of tile low rank. So there's the original operator. It never needs to be formed and stored. It can be created on the fly from correlations between the original particles or the original observation stations. And this is linear growth. This is matrices growing from 16K to 1 million by 1 million. So again, this is a 4 terabyte construction if dense, but it lives on a single GPU because it's been sparsified. And what you see here are 2 precisions. Dashed is double, and dashed is dashed is double, and solid is single. And then the 3 different colors are different implementations of the hierarchical low rank algorithm using the Kublas or using Waji's efficient kernels and eventually streaming. So down is good in this case. Here is an illustration of how much of the available bandwidth is able to be exploited. This is the peak bandwidth for that old GPU, and you see that the streaming version of the hierarchical MATVEC in HICMA, it gets a very healthy percentage of it compared to the original Kubla's part. Of course, that's one vector. What about if you have multiple vectors available at the same time? You get good amortization. It's not quite linear in the number of vectors, but on the GPU, it stays quite healthy on the way up. And that is reflected in this distributed hierarchical GEM-V on 1024 GPUs of Summit, where this is respectively 1, 2, 4, 8, up to 64 vectors. And that actually achieves, by the time you get to 64 vectors, you're essentially hitting the GEM peak for that particular GPU. And getting relatively good scaling. So what about H multiplication? Not matrix vector, but matrix matrix. This can be cast as the problem of constructing an H matrix from MatVex. And these are two examples with two different tolerances for the recompression of the original matrices. This is n log n. We do expect an n log n operation count, and it is tunable by the accuracy with which one wants to recompress. And that can be that directly affects the number of samples of the MatVec that need to be considered. With these fast MatVecs, we can do fast approximate inversions with Newton-Schultz. That can be used as a preconditioner in a Krylov method. So this collection of tile and hierarchically low rank algorithms and a description of their software can be found in this paper. And I suddenly realized that I'm heading to the end of my time. So I will just show a couple of applications in movie format, if you will. And I apologize for that. But one thing that we have been working on is, Hessian-based optimization, PDE-constrained optimization, particularly for subsurface examples, but for quite a variety: transient diffusion, stationary advection diffusion, time domain, E&M, and frequency domain acoustics in a variety of subsurface applications where the very large Hessian is implemented with the hierarchically low rank matrix algebra. And of course, the optimization on the outer level is not original. What is the point here is that everything can be carried out with relatively dimension invariant linear algebra. And on the frequency problem, it's encouraging that ranks do not swell in proportion to frequencies. So between the brown and the blue, the frequency is doubled, but the ranks at a different level of the matrix hierarchy are less than doubled, which is a key consideration since K cannot be theoretically predicted for this problem. And this is in a recent CISC paper with our friends at Texas Austin. In fact, in Karen Wilcox's group. I guess she was the speaker last week. One more example is fractional diffusion. This is an evolution equation of a fractional diffusion operator. So Laplacian to the alpha over 2. It's a dense matrix, but its limit as alpha goes to 2 is the sparse Laplacian. So it has data sparsity, and that data sparsity is reflected in extremely good compression for both the elliptic and the parabolic case of space fractional diffusion, attaining linear time for the compression of this operator. And for example, for a 2 million size problem, a couple of thousand degrees of savings in memory. Well, I've hit the end of my hour, and people have to go. That's in a recent CMAIN paper. We're targeting architectures out ahead of where they are, like a falcon does. A falcon doesn't fly to the prey; it flies to where the prey is flying, and that's really the philosophy we have here in being very energy and memory austere. These are my recapped conclusions, some directions that are, I think, obvious next steps, including an infusion of theory to predict ranks and to tune block ranks to overall ranks for a given matrix operation. I love tile low rank and hierarchically low rank. And I love to write haikus for my students. curse of dimension, can you be mitigated by low rank's blessing? And vast sea of numbers, can you be described by few as bones define flesh? And I'm advertising for a few postdocs. Not enough time to describe them here, but we're using tile low rank inversion in Marchenko imaging with Aramco. That's Matteo Ravasi and Daniel Colombo, the latter from Aramco. Send me an email if you're interested. This will start on May 1. And we're recruiting 2 postdocs for a machine learning application matching intermittent power to intermittent demand in the city-state of Neom being built on the Red Sea in the Gulf of Aqaba region of Saudi Arabia, where it will be a carbon neutral habitation roughly the size of Belgium. And there's a lot of machine learning to be done to allocate demand to supply and the rest into storage in this very challenging environment. We have some great sponsors, and I thank you very much for your attention, and please forgive my going over. I see a raised hand. Oh, I see Tim very kindly clapping.
Clapping hands. Yeah, thank you very much, David. Yeah, this was very, very nice. Let me see if there are other questions first before I ask mine. Anybody from the audience?
I can ask a question. So you said this thing about the hawk where the architectures are flying. So what do you expect to see in 5-10 years? Where will we be, the architectures in 5-10 years?
Well, this is a very difficult question for me. I'm not an architect, but Satoshi Matsuoka took it up yesterday. He's the architect of Fugaku, the world's #1 system, which is built out of ARM A64FX chips, not GPUs. Now, Satoshi was the original person to put GPUs into a supercomputer with Tsubame at Tokyo Tech, and he then went to something more homogeneous for his $1 billion latest entry. And he says, contrary to many people in the Department of Energy, that we're not going to be looking at heterogeneous devices where there's one of everything for every domain-specific app, but that we will be going for a very energy efficient and instruction austere thing like an ARM chip with their tensor core, matrix multipliers. Whatever we're going to do, I think we're going to be sacrificing reliability for energy efficiency. I think as algorithmic designers, we should get used to the need not to depend on fully reliable memory reads and writes, but things that we have algorithms that can recover from hardware flaws, and you can always evaluate. You can always allocate a specific part of your device to high reliable memory, high reliable computing, to compute residuals. See whether you went off somewhere. But one thing we're probably going to ask architects for is for more energy efficient devices, even if they are less reliable. An exaflop system is 20 megawatts, 36 at peak for Fugaku. Predicting the climate will change the climate if we keep going at that rate. So I think we have a stasis for a while, near in the infra exaflops, and I think we need maybe some new breakthroughs in architecture, like carbon nanotubes or DNA or something, before we can push further. I'm not an architect, but it's fun to speculate on the kinds of devices that we'll have to migrate our kernels to. By the way, I do think there will be room for a quantum attached processor to do quick, unconstrained optimization or something. It'll be an attached device. It won't be a computer, but it can do a small number of things very fast, and we may be offloading to that. before we see, a fully functional quantum computer.
Mhm. Thank you.
Thank you.
If there's no other question, I'd like to ask mine, which has to do with something that you mentioned, that the codes will be more complicated. And one of the reasons that we all loved BLAS and similar types of routines was because all we had to do was define the matrix and then just send it over to the routine and it would do whatever we wanted. But so how much more complicated will it be for the end user to take advantage of these tools?
Well, I mean, our goal is to provide that kind of an API, relying on the vendors to do what you just said. I mean, the deep level BLAS, those are highly structured, and since we build on those, the vendors carry us there. But connecting, the BLAS on some new exotic architecture to your generalized eigenproblem for quantum chemistry, there's a lot of layers, in there, and better than anyone that there's no standard eigensolver. How many vectors do you need? Are the eigenvalues interior? And so forth and so on. So there's a lot of infrastructure to be supplied there. But ideally, a user who knows what he or she wants should be able to tap into an interface that is fairly architecture agnostic. I mean, there's a lot of work in between, but we should be able to structure the scientific workforce, if a computer is a scientific instrument like a microscope or a telescope is, to provide that level of interface. I think it will always be the case that a user who knows how to cross that barrier can get better performance, but a certain high standard of performance should be available, with default tunings. And that is our part of our goal in HICMA.
Yeah. Thank you. There is one hand, Arthur Young.
Yeah, hi.
Hi.
Thank you for your talk. I have a sort of a more kind of vague question that follows this performance question or the theme that you've been discussing for like the mechanics of your API. But a lot of my experience with research when it comes to the notion of sparse low dimensional objects that exist in higher dimensional spaces has a lot to do with the work from 2006, 2007, compressed sensing, and that whole sort of subsequent area of development. And so I guess my question is, in my experience with using compressed sensing and stuff like that, and basis pursuit problem type things, you're looking for a low dimension, you're searching for a low dimensional signal amidst what is otherwise a high dimensional space. And so my question, I guess, is, can you see more kind of inverse type searching for meaning in data being those types of problems being used by your API?
I have to confess that this is what we're talking about here is a fairly mechanical pursuit of low dimension. It doesn't know find something here or with this shape. Sure. It's not smart like PCA might be, or so in that sense, maybe what we've taken on is an easier problem than compressed sensing. When a physicist knows there's a low dimensional manifold to which everything goes, it's not necessarily easy to find it. Now, I was recently reading a proposal that I shouldn't, I don't even remember who wrote it, so I shouldn't betray confidences, but evidently there's a lot of hope that machine learning can be supplied to find low dimensional objects in gravitationally induced structures, in cosmology. And I would assume that the connection between what the very noble thing you're seeking and the very sort of mechanical thing that we're offering would be that if that is the case, then hopefully the kernel matrices of machine learning and the convolutional operators of neural nets can be speeded up at their innermost by taking advantage of algebraic compression.
Yeah.
Whether that is redundant, I don't know. In other words, if you're smart enough to know what you're looking for in the first place, you may squeeze it out before you get to the linear algebra. But if you're able to reduce the outer problem to a sequence of dense linear algebra problems, maybe we can help there.
Right. Yeah.
And when I say we, I'm one of literally hundreds of people working in this area. And it's a very hot topic in numerical linear algebra. Now, it might account for like half the talks at the SIAM NLA meetings, that are on this data sparsity stuff now. So there's so much more to learn if you bring something that's problem specific into your starting point, I think. But it's a great question.
No, that exactly answers what I was hoping to hear. Yeah, thank you.
Thank you.
Okay, let's see. Any more questions?
Those are
I don't,
3 really good questions.
Yeah, I don't see any.
I apologize for not leaving more time for questions.
And it's about, no, that's okay. It was very, very interesting and very exciting what you described. But it's 15 minutes or almost past the hour already. And I would like to thank David again for a wonderful presentation and for coming to visit us virtually. Hopefully we'll see him in person soon. And yeah, wish him the best and thank the audience. And thank you, David, again, very, very much for your wonderful presentation.
Thank you very much for your invitation. And until I get to Alston.
Okay. Take care.
Bye.